Hello, my name is Frank Ferro. I'm the Senior Director of Product Management at Rambus, responsible for all physical IP. I want to thank you for taking the time to listen to my presentation about powering AI ML inference with GDDR6 memory. I want to start this presentation by looking at the memory requirements across the internet. And I want to start with the cloud. And most of the heavy-duty computing is done in the cloud, especially around AI training. And AI training these days has really been heavily influenced around the need for generative AI. So that's driving increased size in models and increased compute power. So if you look at the requirements associated with those large AI models, you'll see greater than terabytes per second of memory bandwidth performance. So in this case, you just can't get enough memory. And more and more activities are moving up into the cloud. So the cloud, of course, the infrastructure is growing, and the need for compute just is unrelenting. And so a lot of the compute is moving toward the edge because of the fact that you don't want to have to push everything up into the cloud. So the edge, if you look at the edge of the network, is actually starting to look like a data center in and of itself. So at the edge is where we're going to do some more lighter weight AI training processing. But along with AI training, we're going to also do AI inference. And just to define training and inference, so training is where you take an image or language or whatever you're trying to identify, and you train those models. And typically that's done in a non-real-time environment. It takes days and weeks and months. But once the training is complete and it's good quality, then you can kind of push those models out into the edge of the network and even into the endpoints of the network. And that's where we talk about AI inference, where we would infer or identify what those images or whatever you're trying to do, whether it's finance or language. So the edge is where that happens, and the edge has a little bit stricter requirements from a cost and performance standpoint. And so there we see memory performance is in the 300 to 500 gigabytes per second. So again, less memory bandwidth needed, more power efficient, more cost efficient. And then finally, some of those models gets pushed down into the endpoints of the network. And this is where you see more of your consumer or embedded devices. And here again, you even have more stress on cost and power efficiency. So the typical memory bandwidth needed at the endpoints of the network is going to be 50 to 100 gigabytes per second. So depending on where you reside in the network is going to influence your choices of your memory type you're going to use, the cost, and the power performance around that memory subsystem. So because of the processing requirements, so even if you look at the endpoints, you still have 100 gigabytes of performance needed. So the processors that go along with those, are still not getting fed enough memory or has the efficiency they need. So we look here at the types of processors that are being used in the network today. So at the cloud, the GPUs continue to dominate, and the larger, up in the 90% of the market, most AI training is done on a GPU. But you can see over time, there will be other application-specific processors that are going to be developed that would give better efficiency. So as the AI market matures, as the applications mature, then you can start to target very specific dedicated processors for those AI models. But even still, the GPUs are probably not going away anytime soon in the data center, and still we see those dominating for quite some time. At the edge, however, especially when you're doing either lighter training or inference, we do see more and more custom processors, or at least the transition to dedicated application processors moving into the edge of the network. And again, you see this still, pretty dominated by GPUs, but over time, due to cost and efficiencies, we're going to see dedicated processors. And many companies are working on processors that for their specific types of applications, and whether it's AI training or inference. So you can see the shift, and with this shift is going to come very specific memory bandwidth needs. So what kind of applications do we see at the edge, and then what does that impact on the semiconductor market? So the applications are just pretty limitless. We see all kinds of around the compute. Okay, there's augmented reality. You see voice and image recognition. We see trading at the edge of the network for sure. In networking, monitoring, load balance, virtual machines. And in the storage segment, you'll see more database acceleration and compression at the edge, even different sensors, medical and weather processing. So a lot of applications going on. And again, this is putting on high demands at the edge for edge computing market. And what we're seeing in the past, you had more, the edge is really moving data through the network as opposed to processing it. So we see more inline compute at the edge of the network, and there's certain advantages to that we'll talk about. But if you look at the right side of the chart, you can see on the bottom that clearly semiconductor, the training chips are the largest volumes in the data center, although there's still the need for inference, and that's continuing to grow. But if you look at the edge of the network, the top right chart, you'll see that the number or the semiconductors at the edge for AI inference is certainly dominating the cloud market. So again, we continue to see lots of new designs and designs, architectures being used at the edge. So what are some of the advantages of edge computing? I think the first advantage is that it does reduce your transactional latency. In other words, if you don't have to move things as far, so from an endpoint to the edge, it's going to speed up. And of course, today we need instant response from our electronic devices, and any delays are not tolerated. So you get better latency, better throughput. The other thing it does reduce the pressure on those along all links, because you're not moving as much data. Today we're talking about memory, but Rambus also provides high-speed SerDes links that go into the connectivity in the network. And like memory, we see constant pressure to get faster and faster SerDes links, serial links on the networks, whether you starting at 25G to 50G to 100G to 200 plus G on the network. So it does reduce some of the stress by not moving the data around. And power is a big concern in the network. So by moving data, every time you move data, it costs power. And so by doing your processing in line at the edge, you're definitely going to save power. And then of course security. Every time you move data, you're opening up kind of a new security threat. There's a new place to go and attack the network every time you move the data. So less data movement will also give you a much more secure network. And then again, doing training at the edge also helps take the pressure off the cloud, and it improves overall efficiency and performance in the network. So what are some of the type of memory choices that we have? And everyone should be familiar with, if you're doing any kind of system design, with DDR. DDR has been around forever. It's still the dominant memory in the server market. And it's a very good high density, good cost efficiency. LPDDR has traditionally been used in the mobile market for your cell phones and tablets. But because of the speed of LPDDR, LPDDR4 and 4X is 4.2 gig, and now as you move into LPDDR5, you're going into much higher speeds. LPDDR looks like a good memory solution for some of these AI applications, especially at the edge, because it gives you good cost, good density, and good power efficiency. And then if you're in the cloud and you need that terabyte performance, HBM is the memory of choice. And if you were tuning in earlier, or if you want to go back, I gave a presentation on high bandwidth memory for use at generative AI in the cloud. And you can take a look at that. You can dive in deeper. But HBM certainly gives you the most bandwidth. It gives you the very good density, good power performance, but it is a bit more complex and expensive. You can see here in this picture, you have a 2.5D structure, you have 3D DRAM, and you have to put all that together. So the industry is maturing in this 2.5D, but there's still some ways to go. And what we want to focus on for the edge in particular is GDDR, and you're thinking, well, GDDR is graphics memory, and that's true. It's tried and true for graphics processors for gaming. However, GDDR, like LPDDR, has much higher performance than DDR. So DDR4 is at 3.2 gig, where GDDR is at 16 gig and beyond. So you can see you're getting 4 or 5 times the memory bandwidth with GDDR. So you say, well, it's great for graphics, but I have an AI inference and I don't want to go through all the expense of using HBM for inference. GDDR looks like a really good compromise and trade-off between these memory systems. So we can look at an example. If you're going through the process of picking a memory system, these are some of the choices and some of the trade-offs that you might want to look at. So here, I said, all right, we've got an AI inference system that needs somewhere around, let's say, 350 gigabytes of performance. In this case, we picked LPDDR5X, we picked GDDR6 and HBM3 to compare how these memories would perform in this particular system. So we look at LPDDR5X running at a pin rate of 8.5 gigabits per second, which is the high end of the LPDDR spectrum. You say, well, I would need 12 of those. The interface on LPDDR is a by 32 interface. So if I do simple math, I can 12 by 32 is going to give me the bandwidth I need, so 384 gigabytes per second. And you would need, like I said, you can need 12 of those, but they also come in packages that are where you can get 2 in a package. So you may need, at least 6 packages of by 64s, but regardless, you're going to have 384 pins. So you're going to have a little bit larger board, and that does potentially create some challenges on your physical implementation. If I'll jump to HBM for a minute. So HBM, even one HBM3, provides you significantly more bandwidth than you need. This gives you 820 gigabytes per second, even at the slowest HBM rate of 6.4. So you can see it does the job and then some. It has very good power, very good board area, but you're going to pay, it's expensive you're getting more bandwidth than you need, and you're going to have to pay for that whole 2.5D structure. If I look at GDDR now, GDDR6 at 24 gig, which is the highest performance point of GDDR, you can see with only 4 physical layers and 4 DRAM, I can't hit that 384 gigabytes per second. So I'm getting significantly less pins. I'm 4 devices, 128 pins. And so I'm saving board area. I'm going to be saving overall system cost. So this is one way to look at if I've got an inference problem. LPDDR could be a good solution. GDR could be a good solution. HBM might be a bit of an overkill, but again, it really depends. So this is a way you can look at, pick your bandwidth, and then we can work backwards to find out what the best memory solution is going to be. So looking at this from a product perspective, I wanted to look at a couple of AI cards that are used for inference. So this is these are two cards. One is Inflame Cloud Blazer. This is stands for Inference, the i10, and this gives you a good amount of performance, 70 teraflops of performance. And then this one uses this particular card uses two HBM DRAM. So that gives you 512 gigabytes per second of performance and 16 gigabytes of capacity in terms of store memory. Another card we look at is the Acronix Vector Path. And this card also gives you very good performance, 86 TOPS operations. And this one uses GDDR6, and there's 8 of them. So in the Cloud Blazer, you use HBM. In the Acronix card, they use 8 GDDR6 that gives you the exact same memory bandwidth, and it gives you the exact same capacity. So here's two different companies' ways of solving that AI inference problem. You can use slower speed HBMs. You can use GDDR. They both solve the problem that you're trying to accomplish. You can see for these applications, they are doing AI inference in the cloud, but they're also doing AI training. So this covers a wide range of applications at a much lower cost point. If I look under the hood of the Acronix, you can see the block diagram on the right-hand side of the FPGA. So you can see there's 8 GDDR6s. You've got 4 on each side, giving you 4 terabits per second of total memory bandwidth. So again, this was you didn't have to go with the 2.5D structure. You can see they've got SerDes coming in, and so they're filling the system with pumping data in through long reach and PCIe, and then you've got a longer reach SerDes on there. So you've got lots of data getting pushed into the device. You've got a lot of processing power through the GDDRs. There's even DDR on there for local storage. Again, gives you plenty of compute power, plenty of bandwidth, and it keeps it into a relatively lower cost environment by not having to go 2.5D structure. So let's look at the GDDR6 memory subsystem itself. So what are some of the advantages of using a subsystem? First of all, you've got 2 pieces. You've got your physical layer, and you've got a memory controller. So the physical layer, typically at Rambus, we deliver that as a hardened IP, and that talks to the DRAM. And then you've got the memory controller that's talking to the system bus. And if you look at the controller, you can see the blocks are, and this is delivered as soft IP. Please jumped ahead of myself. So the soft IP is configurable RTL, and talk about why that is. But you've got all these lighter color boxes, and every application you see, depending on what kind of neural network or kind of inference you're trying to do, you're going to want to tune that memory controller for your specific needs. So the type of interface you need, whether it's AXI, whether you want to use multi-ported front end, if you need read, modify, write core, if you need ECC. So those are all configurable blocks. And what Rambus does is we work with our customers. They can take the controller, look at the requirements in terms of how much, for example, how much buffer memory you would need, what kind of from a system simulation standpoint, you can take your data, you can pump it through. We can even simulate the PHY, and then slowly tune the system to see what's going to give you the optimal memory. And typically, we'll see memory systems performing in the high 90s from an efficiency after we've gone through some iterations. And so once you've got it tuned up and you've got very high memory efficiency, then we'll take that whole subsystem, we'll validate the PHY and the controller, and deliver to you as a single block. So this is convenient. So as a customer, you don't have to validate the PHY and controller. We do that for you. You've got one point of support for the entire subsystem. So we can look at the controller a little closer. And again, I talked about you have all these configurable blocks. You have, again, supporting up to 24 gigabits per second. So we do, again, timing. A lot of companies worry about timing closure, so we lose the timing closure at those high speeds. We also have the ability to do test. I didn't talk about, we have memory test analyzer. And so you have multiple ways to test the system. You can look at your memory transactions through the test analyzer. On the physical layer side, on the PHY, we also have ability to do testing. So you get complete system test. You have multiple configurations for the controller. Again, depending on your system, you may want to instantiate a dual controller. You may want to instantiate a single controller. At the highest speed rate, I mentioned we do timing closure. The controller runs at 1.5 gigahertz clock operation for 24 gig if you're going to be running at that speed. We also have inline ECC. And I'll talk about that more in a minute, but when you're using a GDDR, you can't do out of band, and so we help manage the ECC. So with DDR, typically, the way you want to do ECC is you would add another DRAM on. So that's, we call that out of band. So you'd have a by 64, and then you add another 8 bits, and that 8 bits would be used for error correction. But that's not practical with memory systems like GDDR, because we've got a 32-bit wide interface. So adding another DRAM on there is not practical. Very similar configurations for LPDDR. So instead of having the out of band, then we take some of the bandwidth from the system, so the memory gets divided into smaller segments, whether if you're using 32 bits of memory or 16 bits of memory, and then we would take those segments and use one of those segments for error correction. And so we try to minimize the impact of your performance with inline ECCs. Again, it's going to take away a little bit of your bandwidth, but depending on your data traffic, hopefully it should be negligible. So we can dig into the PHY a little bit more. So if you look at the physical layer, we have, as I mentioned, it's hardened and timing closed. And again, that's very important. You don't have to worry about anything like putting a decap on. So all the I/O, all the decap is done for you. It's completely timing closed. So very easy from a system integration standpoint. From a physical design, we also provide, now you're running these signals at 16 or 18 or 24 gigabits per second. So doing your PCB, although it's not an interposer, you still have a traditional PCB, but getting a good signal integrity in your PCB at 24 gig, typically you're going to need some assistance. So what we do is we would provide on the PHY side a reference design for the PCB, the type of materials and the how those traces look. We also provide a package reference design as well. How do you escape these high-speed signals from the package? At the bottom there is one of our development environments. So we have multiple boards for our GDDR. We have this particular board is one of our test boards. We have multiple sites on that. And we also have another board that has even, what we try to do is give the lowest cost materials to show you even with a low-cost material, you can still run GDDR at the maximum speed. And again, there's not. I think right now 24 gig is the top. Not many vendors can support that level of performance. The PHY also so it gives you the highest bandwidth for GDDR at 96 gigabytes per second. We also, though, again, power is a big deal. So we've this is into our third generation of GDDR, and with every generation, we continue to put more and more power control into the device. So this latest version has significant power management. So even though you're running at very high performance, you have the ability to throttle the power and to whether you're running full out or whether you need the PHY to idle, we can manage the power very efficiently. And then finally, on the from a density standpoint, the IP supports is called clamshell mode, and this is a way to increase the density by you can put two DRAMs together, and so increase the density, but at the same bandwidth. So the PHY supports that, so it gives you good performance, good density, and we give you all the support material on your physical interface. So just want to talk a little bit more about the signal integrity. And one of the key things you've got on the left-hand side, you have all of these different signal integrity attributes, whether it's insertion loss, reflection, crosstalk, and then you've got to do your physical design to minimize those effects. So you can see this example on the right side just shows something as simple as back drilling your and being careful about those stubs can go from from an eye that's closed to the eye that's open. So with GDDR, care has to be taken at every step of the way. It's not just the PHY, but your physical design is very critical in terms of getting the performance you need. So I wanted to talk about just the advantages of using Rambus GDDR6. And we have a lot of experience. We've been doing this. We had all the way back to GDDR5 in 2010. We were the first to come out with a commercial 16 gig product, first to come out with 18 gig product. And our latest 24 gigabits per second is industry leading. So we have a lot of experience working with us. We have a very strong tools environment. We have a very strong support team. So we'll make sure that you can get the performance you need, and we'll help you every step of the way in your design. Before I close, I just wanted to, I mentioned that Rambus also has a complete portfolio of not only memory products of HBM, LPDDR, but also SerDes products for PCIe and CXL Ethernet. And for the 5G infrastructure, we have JESD and CIPRI. And for the consumer and automotive, our MIPI products. So again, a complete line of products. So in summary, again, we see continuing demand for AI, whether you're doing it in the cloud, at the edge, at the endpoints of the network. And depending on where you are in the network is going to drive your memory requirements. For GDDR6, we see as a perfect solution in the edge because it gives you that balance. At 24 gig, you get quite a bit of performance, but you also have a good cost profile with the memory. So for AI inference, GDDR6 is the way we see to go. We have many customers using it, so Rambus has experience across many applications, not only graphics, networking, and AI. And we provide the full subsystem. So again, validating the PHY and the controller, so you don't have to worry about doing that. And then finally, we give you all the tools from system design, PCB package, and we also have experts. We're an SI company, and we give you access to our SI experts as you're going through your whole design process and through the bring up. So I want to thank you for listening in, and you can ask us questions online or at rambus.com. Thank you.